Get ready because today we're diving into some seriously mind-bending stuff, like universe rewriting stuff. We're talking dark matter, that invisible enigma that's everywhere but nowhere.
Yeah, it's a real head scratcher. Astrophysicists have been trying to pin it down for decades. We see this X all over the cosmos.
Right, like it's holding galaxies together, but we still can't figure out what it's made of. It's like the universe's best magic trick.
Exactly.
But what if, and here's where it gets really wild, what if dark matter isn't some elusive particle at all? What if it's something woven into the very fabric of reality?
That's the mind-blowing idea we're tackling today.
We're going deep on theoretical physicist Eric Verlinde's 2016 paper, Emergent Gravity and the Dark Universe.
In this paper, he suggests that dark matter might not be matter at all.
Whoa, okay, so where do we even begin with that?
Well, imagine space-time, not as this empty stage, but as this kind of cosmic network woven from information. Every thread, every connection is a piece of information.
Okay, so not just an empty backdrop, more like a giant cosmic tapestry, and we're all connected.
Exactly. And it gets even cooler. Verlinde saying this network, it's not static, it's constantly changing. Every time information is rearranged or displaced, it's like those threads in the tapestry are being tugged and stretched.
Hold on, I'm trying to visualize this. Are you saying those tugs and stretches are what we feel as gravity?
You got it.
So wait, instead of invisible particles pulling on stuff, it's more like the universe is this giant rubber sheet. And when you put something on it, like a bowling ball, it distorts the sheet.
That's a good way to think about it. But here's the key difference. It's not just about matter sitting on this cosmic fabric. It's about how matter interacts with the information that makes up space-time itself.
Okay, so it's not just being there, it's messing with the very structure of things. How does this explain the whole missing mass problem, though? Where does dark matter fit into all of this?
So remember how we talked about information being rearranged? Verlinde says that when matter appears, it's like we're disrupting this network. Imagine deleting or moving files on a hard drive. You're changing the information landscape.
So matter, just by existing, is messing with the universe's file system, essentially.
Exactly. And that information displacement, it doesn't just go away. It leaves a kind of imprint or memory in space-time.
Okay, this is a lot. So you're saying that every time a star forms, even when we move around, we're leaving a mark on the universe by changing how information is arranged.
Yeah, kind of. And those marks, those little disruptions, are what Verlinde believes we experience as dark matter.
So dark matter isn't some weird invisible particle. It's a side effect of the universe remembering everything that's ever happened.
In a way, yes.
Wow, that's a lot to take in. But if it's true, that changes everything. It means dark matter isn't something we've been missing. It's a fundamental part of space-time itself.
Exactly.
Okay, so how does this hold up against what we actually observe in the universe? All right, so this is all super interesting, but like any good theory, it's got to hold up against the evidence, right?
Absolutely. And one of the biggest pieces of evidence for dark matter comes from how galaxies rotate or spin.
Right, like those spiral galaxies we always see in those incredible pictures from space. They're spinning so fast they should be ripping themselves apart.
Precisely. Based on the amount of stuff we can actually see in those galaxies, stars and gas and all that, they should have flown apart eons ago. But they haven't.
Yeah, it's like something is holding them together, right?
Yeah, exactly. Some invisible cosmic glue.
And for the longest time, astronomers have been saying that glue is dark matter.
Exactly. But get this. Verlinde's theory can actually explain these super fast rotations without needing to use dark matter at all.
Really? How's that even possible?
Okay, so remember how we were just talking about information displacement? Imagine a giant trampoline, like cosmic-sized, and you put a bowling ball right in the middle.
So the bowling ball is like a galaxy, and the trampoline is our information network, right?
Exactly. The bowling ball makes a dip in the trampoline, right? That's kind of like the gravity from the stuff we can see in the galaxy, the stars and gas.
Okay, I'm with you so far.
But here's where it gets cool. Verlinde's math, it suggests that the act of making that dip, of displacing the fabric of the trampoline, actually creates a sort of pushback, like a kind of extra gravity.
So it's not just the bowling ball itself, it's the fact that it's changing the shape of the trampoline that's adding to the effect.
You got it. And what Verlinde found is that this extra gravity, this pushback, it's strongest at galactic distances. It's like the trampoline is most sensitive to being distorted at those scales.
Okay, this is wild. So just by having matter and energy, galaxies create extra gravity, and we've been calling that dark matter.
That's what Verlinde is saying. And here's the kicker. When you actually use his equations to predict how fast galaxies should spin based on what we can see,
Hmm.
the results, they match up incredibly well with what astronomers have been observing.
So it's like we've been trying to solve this puzzle with a missing piece, but Verlinda's saying, hey, what if there wasn't a missing piece? What if we just weren't looking at the picture the right way?
Precisely. It's a totally different way of thinking about things. And it's not just galaxies. This idea has implications for the entire universe.
Okay, my mind is officially blown. And I know I keep saying but this extra gravity, if it's supposed to be everywhere, shouldn't we see the effects even more strongly in places where there's a lot of matter crammed together, like in galaxy
That's a
clusters?
very good question. It's one a lot of physicists have been asking about Verlinde's theory.
We're talking about those massive clusters of galaxies, right? Like hundreds or even thousands of them all crammed together.
Exactly. You'd think if matter messing with information is what's causing this extra gravity, then those clusters, those would be like the ultimate test case.
But they're not.
Well, it's tricky. Verlinde's initial calculations, they worked incredibly well for single galaxies. But when you look at those galaxy clusters, his theory seemed to come up a bit short, like it couldn't quite account for all the gravity holding them together.
Okay, so is that it then? Is Verlin's theory wrong?
Not so fast. You see, those first calculations, they were based on a simplified model of how matter is spread out in a cluster. It's like assuming all the mass of a galaxy is, like, concentrated in a tiny point at its center.
Right, like when we were talking about the bowling ball on the trampoline.
Exactly. But in reality, the matter in a galaxy, it's spread out over, well, vast distances.
Ah, so it's like trying to calculate the Earth's gravity by pretending our entire planet is like squeezed into a marble.
Precisely. And that distribution of matter, it changes things. Verlinde argues that if you factor in how matter is actually spread out, clumped here, more diffuse there, then his theory might still hold water.
So the jury's still out on whether this whole information-based gravity thing can really explain the universe on the grandest scales.
Exactly. But even if his theory needs a little tweaking, the implications, they're still huge. Just thinking of the universe as this interconnected web of information, where our very existence is woven into the fabric of space-time, it really changes how we view everything.
I'm still trying to wrap my head around it all, but I have to say this has been one of our most mind-blowing deep dives yet. Starting with this question of what is dark matter, and ending up talking about the fundamental nature of reality. It's incredible.
And that's what makes these conversations so fascinating. We're always learning, always pushing the boundaries of our understanding. Verlinde's work is a perfect example of that. It reminds us that even our most established theories, they can always be challenged, refined, maybe even completely rewritten.
So where does that leave us? If our listeners take away one thing from our deep dive into emergent gravity, what would you want that to be?
I'd want them to remember this. The universe is far stranger, far more interconnected than we often give it credit for. Our search for dark matter, it might not lead us to some exotic particle. It might lead us to a completely new understanding of reality itself.
And that's a journey I'm definitely here for. That's it for today's deep dive, everyone. Keep those thinking caps on, and we'll see you next time for another exploration of the universe's greatest mysteries.